Sure. And let me tell you
Yeah.
this. I'm organizing the Berkeley seminar, and I made the same mistake, and we have a speaker right now speaking, and probably the attendance will be low as well. Uh,
Okay.
so
Yeah, I'm sorry. I really didn't notice.
me neither.
I am, yeah, I am not familiar with any holidays
Me
at
neither.
all.
I'm not American. I'm from Israel, so like it was a surprise for me as well.
Right.
So
So
good.
sorry about that.
Yeah, no
Right.
problem.
Okay. So let me introduce you a little. So we are happy to have today Ofri Telem as our speaker. And he's currently at the Berkeley Center for Theoretical Physics at the University of California. Um, and he's going to tell us about what is the name of these action strings are superconducting. Wait, action strings. I have the title here. Oh, action strings are superconducting. Sorry about that. So thanks for accepting our invitation. Welcome, and the floor is yours.
Thank you so much. So let me first comment on the title. So axion strings are superconducting. As I said the same thing when I last gave this talk. This is kind of like Schrodinger's fact. It's something that half the people will tell you that it's obvious and they've known it since the 80s. Uh, Now, I was only born in the very late 80s, so I learned this fact recently. And half the people are going to say that they didn't even know or think about it in cosmological contexts. So we're going to explore that fact and whether or not it has direct implications on the network evolution of axion strings in the early universe. Good. And you know, I also want to emphasize that thank you so much for the invitation, and it's an experience to speak here at the lion's den of primordial magnetic fields and cosmic strings. So I also expect to learn today from members of the audience. So let me give you the quick upshot. This is like a one slide summary of what I'm talking about. So the key mechanism that makes axion strings superconducting is called anomaly inflow, which is something that kind of resembles the quantum Hall effect and was explored by Callan and Harvey in 1984. This is different from Witten superconducting strings, which are not anomalous. Their anomaly cancels between two types of charge carriers with opposite chiralities. This is a chiral superconducting string. Now, what we explore in the paper is two things. The first thing is we just looked at the cosmic evolution of axion strings, and we didn't assume that they're embedded in primordial magnetic field or anything of that sort. And so naturally, we just assume that there's some electric field generated along the strings, which is comparable to the temperature. So it kind of leads to a current on these strings that's comparable to the temperature. Now that has no seeming consequences to the network evolution of axion strings or the relative density today, but might uh, have, enable the creation of stable vortons. Now, whether or not the vortons are stable is a particle physics question. It depends on the leakage of current from uh, string loops, and we'll explore this. In what part of the parameter space we might get stable vortons. The second part is directly related to the axion relative density. So if we just assume a primordial magnetic field from inflation or from phase transition in the early universe, we naturally get maximal currents on the axion strings, which are comparable to Fa of the PQ symmetry. That could also lead to vortons, but more interestingly, it can lead to modified string evolution because there's a dominant new friction force on the strings from the plasma around them. And this greatly modified string evolution, basically the number of strings per Hubble can be 10 to the 4 to 10 to the 6 more at the QCD phase transition. That could lead to a big change in the axion relic density. So this is phenomenology that's very relevant for axion searches, potentially, if our conclusions hold. So that's the upshot. And now the rest of the talk is just, taking these ingredients and putting them into like formulas and plots. Any questions so far? Good. So I'll start with some forgotten lore, and I'll remind you or tell you why Axion strings are superconducting. Then I'll talk about the Vorton part, which is sort of model independent because we don't assume some PMF generation mechanism. And then we'll switch gears and we'll talk about Axion strings embedded in a primordial magnetic field and talk about the enhancement and their number. And finally, we'll talk about the QCD Axion relic density. Let's start. Axion strings are superconducting. So one well-known fact that's known since the days of Jakiv and Rossi in '81 is that Axion strings have chiral massless fermion zero modes. And this can be seen by just solving for their wave functions in the presence of the string. Of course, you need some Yukawa coupling between the fermions and the scalar making up the strings. But for example, for the QCD axion in the KSVZ model, the KSVZ fermions do couple to the scalar that makes up the string. And naturally, they get zero modes on the string with a width that's comparable to the width of the string, which is the inverse FA. Now, because of the winding of the axion around of the VEV around the string, the zero modes are chiral. So they're kind of like domain wall fermions, and their existence is also given by an index theorem by Eric Weinberg. The interesting thing is if you look at it from the world sheet point of view, now you have a theory with a chiral fermion.
Sorry, can I just interrupt for, if you go back, so what is this, that the Peche-Quinn field must couple to fermions? I mean, must give masses to fermions?
Yeah, because it's part of the KSVZ axiom.
I see. But so is it a model dependent statement or is it a general statement?
It's a general statement that you got to have some field that couples to the PQ breaking field. So in DFSZ, this role will be played by the standard model fermions themselves.
I see.
Right, but
Okay.
something has to couple to the axiom.
And psi, the standard model fermions. Okay.
Here, psi is the KSVZ fermion with mass around the PQ around FA. So it's a very heavy fermion, but on the string it has a zero mode, so it's practically massless.
And is it does it have electric charge, electromagnetic?
Yeah, that's a good question. So when we want to build a cosmologically viable model, we have the two further constraints. One, unless we do some extra model building, we want the number of domain walls to be 1, because we want the QCD axion strings and domain walls to be able to annihilate at the QCD phase transition. Otherwise, they're going to overclose the universe. So that puts one constraint on the model building. The other constraint is that we want the KSVZ fermions not to be cosmologically stable in the early universe, because they're going to overclose as well. So the easiest way to ensure it is to enable a Yukawa coupling. So there's a good review, which actually we just, I gave you the archive number for before I started the talk, that surveys all the different variants of KSVZ and DFSZ models, which are consistent with these cosmological constraints. And in all of them, the KSVZ fermions have to couple electromagnetically. Yeah. So in the sense, it's linked to other constraints, but it is model independent in the sense that you can't come up with a model which doesn't do it.
Okay, thanks.
Sure. Good. So now if you look at the world sheet theory for the fermion and the string, it looks like 2D electromagnetism coupled to a chiral fermion. So it's going to have an anomaly. And the anomaly is what you see here. So that's a mystery. What happens? It looks like in the presence of a background electric charge, charge keeps appearing on the string, and we know that charge has to be conserved, so it has to come from somewhere. And the resolution for this paradox is what's called anomaly inflow. There's a radial current, a Goldstone-Wiltshire current, flowing from the bulk. It's very similar to a quantum Hall current, only the dimensions are a little different, but it's essentially the same problem. And what happens is charge flows radially and then flows along and then feeds the charge on the string. And the way to see this anomaly cancellation is to write an effective coupling, which is similar to AFF dual. So in the bulk, it's just the Axion coupling AFF dual. But on the string, this coupling has to be 0. So what you write is an effective theory where you interpolate between the AFF dual term in the bulk and 0 on the string. This is the way to write it. And I want to emphasize that this is not like a model-dependent thing. This is just a regularization technique to make the anomaly cancellation more transparent. So there's nothing model specific here. And then you calculate the 4D electromagnetic current, and it has a component which goes radially into the string. This is the Goldstone-Wiltshire current that you get by calculating the loop of fermions in the background E or B field. And there's just an Axion current. This is just current from Axion electrodynamics, which goes parallel to the string. So basically what you get is the Goldstone-Wiltshire current from the bulk feeding both the Axion current and the zero mode current on the string. And when you calculate the divergence of this current, you find that it goes like this quantity, TR V effective B theta A, which is just a delta function on the string. And when you sum up all the contributions, you see that there's exact anomaly cancellation. So the divergence localizes on the string and exactly cancels against the divergence of the zero mode current. So that's anomaly inflow. Now, if you take the zero mode current plus the Axion current, that's a localized current going parallel to the string. It has a divergence which goes like easy. And when you squint at it, you see that this is very similar to the London equation or what Witten derived for non-anomalous superconducting strings. The interesting thing here that is different from Witten is that Witten only has the part where the current grows as a function of easy. But because of the anomaly, the strings actually get charge deposited on them. So the current grows and the charge grows as well. And there's a little bit of a question if this alpha between this proportionality between the current and the charge is 1 or not. It's 1 for the zero mode component of the current, but it's not necessarily 1 for the Axion part of the current. And this is why I'm generically putting it to be like between 1 and 2. So for example, in the paper by Agrawal et al., which came out a little bit after us, they claim that this alpha here is 2. But this is inconsequential because we're going to talk about orders of magnitude in our work. So neglecting order 1 coefficients and also the self-inductance of the string, which you can calculate and ends up being something like 0.8, you get basically a superconducting equation here. And as many of you know, if the string just moves through a background B field, it's going to have in the string frame an E field along the string, which means that strings, Axion strings that travel through a magnetic field get currents induced on them. And the different thing is from the superconducting strings that we know and love is that they also have charge deposited on them. So let's look a little bit about the current evolution. So there's this superconductivity term that makes the current grow. In the early universe, there's also a redshift term. And there's also a particle physics leakage term. And this has to be there because I told you that for cosmology's sake, the case VZ fermions in the early universe better not be stable. So they should have generically a Yukawa coupling with a standard model Higgs and a standard model quark. And this Yukawa should be uh, larger. I mean, a priori, we don't know what it is. It definitely doesn't have to be order 1. And as a matter of fact, from cosmology, it just has to be larger than 10 to the minus 15. That's all we need. But generically, there is this leakage Yukawa. So now let's look at the particle physics that could lead to leakage of current off of the string. So one thing, sorry, before I go into these processes, I just want to comment here, because the zero mode on the string is chiral, there's no scattering between like two oppositely going zero modes that can leak into the bulk, which is something that you see in Witten's paper or in work by Barr and Matheson. So we don't have that here for the chiral zero mode current. What does lead to leakage? So trivially, it's just a plasma particle that's incident on the string and just gives it enough energy to go through an off-shell zero mode into standard model particles. So that process will be suppressed because the plasma particle has to hit the string. So you pay the price of the geometric cross-section of the string. And this is what you get. It goes like the parallel because somehow the zero mode has to go into the standard model through this Yukawa. And it's also suppressed by Fa squared, which is the geometric cross-section of the string. The second thing that you have here is you can have a string fluctuation that we describe through the Nambu-Goto boson, describing the position of the string. And this one can hit the zero mode and knock it, cause it to decay into standard model. And here again, it's suppressed by decoupling to the Nambu-Goto boson and also through the off-shellness of the psi star. And let me comment that I was wrong here. Here, there's no off-shell psi. Here, it's a standard model in the S channel, so there isn't a further suppression. Good. So these are the leakage processes, and the leakage is not huge, especially compared to the contribution of the B field, which creates a huge current. So what you should take away from here is that we should address the leakage. The leakage becomes important for photons, but generically in the early universe, there's going to be a maximal current on these strings.
So can I ask something about this anomaly inflow question? I mean, so you said there's some current which is radial, and then it can become a current along the string.
Yeah.
So the opposite can also happen? I mean, if you have a current along the string, can it go leak out?
The answer is no, and I think let me think about the way to see this.
Yeah.
This is kind of asking why there isn't a reverse quantum Hall effect, right?
Yeah, one would think. Well, I know this term violates all kinds of things, but it seems strange that you can have current on it. But yeah, it just seems strange.
Yeah. So let me tell you this. I don't have a crisp answer to give you right now, but I'm pretty convinced that, you know, if we just ask the person who's an expert about the quantum Hall effect, they would be able to answer it right away. The thing is, the one thing that changes is, of course, which way the current bends along the string just depends on the the direction of the winding. But I don't think you can go back into the bulk.
Okay.
Yeah, but let me get back to you on this because this is something that I should an answer that I should have ready. Good. So now let's talk a little bit about the cosmological implications. So this is something that's well known from the 80s and 90s, that when you have a superconducting string moving through a plasma, then you're going to get a friction force on the string, which slows it down. So kind of the intuitive picture is that because of the large current on the string, it creates an azimuthal magnetic field. And then when the string moves through the plasma and the plasma is incident on the string, the magnetic field is going to shock the plasma the way you see it here in the picture. Effectively, it's going to look like a cylinder with an effective radius dictated by the magnetic field. This is called the magnetocylinder, moving through the plasma and incurring friction. And there's a question whether in this context of the primordial plasma, there's turbulence past the string, and I'm not sure what the answer is. I know that in a galactic setting, you're going to have turbulence behind it, but that doesn't really change the nature of the friction force on this cylinder. Okay, so the radius of the cylinder, of this effective cylinder, is dictated by a balance between the ram pressure of the incident plasma and the magnetic pressure shown here. And then when you kind of get the radius out of this equation, you can get the drag force, which is just the density of the plasma, the velocity of the plasma, which is relativistic in our case, the velocity of the string, and this radius of the magnetocylinder. And that gives you an effective drag force that is linear in the current on the string, and an effective time scale, which is the tension, mu, on the string times the string velocity over the drag force. So that's mu over t squared I. And generically, this drag force, what it'll do, it'll make the strings, instead of moving relativistically, they'll just reach a terminal velocity, which is inversely proportional to the current. Any questions about this? Great. And let me comment that this was the cosmological implications for superconducting strings were explored by Dimopoulos and Davis in '99, but they considered sort of a toy scenario. So they didn't consider axion strings. And they also assumed a constant large current, and they didn't think about where it comes from. So the difference in what we're doing here is the application to the QCD axion, and also considering the generation, the dynamical generation of this large current from a primordial magnetic field or from thermal fluctuations. Great. So now we're reaching an important slide. So there's been some discussion since our paper, which I'm not sure what the conclusion for it is. So I would very much appreciate discussing with the audience later about the physics implications of this slide. So what Agrawal et al. Are saying is that because the string has generically a huge charge density, it's going to support one-dimensional bound states around it. And because the charge is so huge, it's going to be energetically favorable for the ground state to fill itself by Schwinger pair production, because the negative energy of the bound state is so negative, it's just energetically favorable. The other thing is that this bound state is generically going to be of radius that goes like the inverse charge density. So it's a really tight bound state. And it can also have a macroscopic occupancy. So unlike the hydrogen atom, where you can just have two electrons, here there's also motion along the string. So you can just populate the ground state with all kinds of standard model charged particles that go along the string, and they will screen the charge of the axion string. Now, the $1,000,000 question for us is, okay, we don't care that much that they screen the electric field because it's in plasma and that's going to be screened anyway. The question is, do they screen the magnetic field? Because if they screen the magnetic field and the effective screening length is of order 1 over FA, then basically the plasma around the string doesn't feel the magnetic field. It doesn't slow down the string, or maybe it does, I don't know. So that's the question. And they're stating without proof that the magnetic field also gets screened, but we're not so sure that that's the case, and we're still thinking about it these days. So, yeah.
Can I just ask, are these fermionic bound states or are they bosonic bound states?
They're just standard model charges. They're like electrons.
Electron. I see. And and Agarwal and company have checked that there are bound states. Like how many bound states are there? And
So what they're saying is that because it's a 1D bound state, they don't even care about the higher bound states. They're only talking about the ground state.
nice.
And they're saying we can throw in this ground state as many electrons as we like. Until, I mean, if you throw enough of them, they're going to screen the charge, and eventually you're not going to be able to add more of them.
But you screen the magnetic field if the charges move along the string. Is that right?
Exactly. So they claim that they move along the string and create a current that's opposite the current on the string, and then together there's screening of the magnetic field. But you know, the stupidest intuition that I can think about is like if you have two wires with the same current, they attract each other. So you'd think it's energetically favorable for them to create a current that only anti-screens the string rather than screens. So I don't have a good answer for this, and I'll be very happy to discuss. But for the rest of this talk, we're just going to assume that there's no screening, which gives us the interesting feeling. Good. So I'm going to assume this and move on, and later I'll be very happy to discuss. Okay, so now we have this huge drag force that goes like the current, and let's see how it affects the network evolution of the strings. So the first thing that you can do is calculate the if there's a drag force, there's a terminal velocity, which you get by comparing the tension to the drag force, because the tension is what's creating the acceleration of the strings as they straighten out in the early universe. And from that, you get a terminal velocity that goes like the drag force over the correlation length of the string, or like 1 over the current. Now, trivially, the correlation length changes with time as v squared L over the drag force. This you can see, for example, this is derived, for example, in the Vilenkin book, or also is in a one scale model. And in our case, if we just substitute the velocity here, it becomes tau drag over the correlation length, which, because the drag force is linear in t, you can right away solve and get that the correlation length is just the geometric mean of the drag timescale and the Hubble timescale. The number of strings in the Hubble volume is t over the correlation length squared. And if you just plug in the numbers, you see that while it's order 1 for scaling, and recently people have been talking about logarithmic scaling violation in the early universe, so it grows until it's order 15. Here, it's I over a critical I given by the tension over M Planck. And this is also the enhancement that you get for row string. Generically, this would lead to orders of magnitude more strings per Hubble. So it could be 10 to the 4 to 10 to the 6, as you will see below. Good. So let me get to the first part. So here we don't assume a primordial magnetic field. We just assume that there's a current due to thermal fluctuations, which gives you I goes like T. And now we're going to ask the question if we have chiral vortons in our scenario. So unlike vortons of superconducting string, which is non-anomalous for anomalous strings or chiral vortons, there's a very simple argument. The stability of the vortons is just due to a balance between their tension that wants to make them shrink, and the electrostatic repulsion that wants them to not shrink, right? So this is the total energy is just the tension times the length of the loop plus the electrostatic energy of the loop. And that thing has a minimum, which you can easily minimize and find it here. Here, whenever you see curly C, that's like the log of FA times or over Hubble, I don't remember. Well, FA times the correlation length. And now, remember that before I said that there are leakage processes, and these leakage processes decouple at a certain temperature. So as soon as these leakage processes decouple, the vortons are stable, and most of them are formed early on. So most of the vortons, of the pre-vortons that will become vortons, are created at this leakage temperature. And I'll show what this leakage temperature is soon. Let's assess the total charge on the vorton to know to substitute it and get its length in vorton mass or energy. So to know what the charge is, we just put in an electric field that goes like T squared. We get a thermal current, a current which is comparable to the temperature. In order to know the total charge deposited on the loop, we have to take the root mean square of the current. So we address the fact that the current generically has a t to the minus 1 correlation length, and that should be divided over the whole loop. So you get a square root of t to the minus 1 over the length. And the length of the loop at its creation is roughly the square root of the number of strings per Hubble times Hubble, all that to the minus 1. And when you plug it in, you find this value for the charge, which is obviously temperature dependent and also dependent on the number of strings per Hubble, which we normalize to a huge number because that's going to be what it is in our case due to the slowdown of the strings. This is the charge on the vortons at their creation, and assuming that charge is conserved, this is going to be the charge on them the whole time. The last thing that we want is to estimate, do a back of the envelope estimate for the vorton density. And then the way you do this is you calculate the total string length that gets emitted into loops at a given time. You get it from the time derivative of the number of strings per co-moving area. You get the total length of the loop divided by the length of the single loop. That's going to give you the number of loops. And that's just going to go like this. K psi, the number of strings per Hubble, over the velocity of the strings, when where K is given by this quantity. I'm not taking you through the whole arithmetics because it's a little tedious. And then eventually you're going to get the vorton density. Now here I'm assuming that these vortons, if there's a vorton and an oppositely charged vorton, they can't annihilate efficiently. But we'll also make the opposite assumption that vortons and oppositely charged vortons annihilate efficiently, and then you get just the antisymmetric component. So these are the results. The dashed line is for efficient annihilation, and the solid line is for inefficient annihilation. And what you see here is the vorton density over the dark matter density as a function of the temperature where the vortons were created. So I said that most of them are created as early as possible, and the earliest that they can get created is at the time where the leakage decouples, because otherwise the leakage is going to lead to the decay of these vortons. Now, what is this leakage decoupling temperature? Intuitively, the leakage happens, all these processes, leakage processes that I described earlier, they went like the Yukawa, coupling the KSVZ fermions to the standard model Higgs and the standard model fermions. So depending on the value of this Yukawa, this leakage temperature could change. right? And so if you just assume an order 1 value, you can get that's 10 to the 2. So here you see that there's literally no photons, right? But if this y is hierarchically small, you can make the temperature, the leakage temperature, rise, and then eventually, well, the leakage is inefficient, so you get more photons, and eventually you scratch the order 1 omega for the photons. Any questions so far? Good.
So this was omega nu, omega dm at the present.
Yeah.
Yeah.
Mm-hmm. Right. Now, the final thing that I must say about photons is that there's an additional thing that we still need to estimate. This is also something that some feedback that we got after we published our paper, which is we assumed that there can't be just a decay of the zero mode because that's forbidden by momentum conservation for the long strings. But rightfully so, people commented that when the Vorton is very small, like of order 1,000 over inverse FA, you can no longer talk about linear momentum conservation. So when you calculate the decay, it's going to look like the wave function overlap between a localized zero mode around the Vorton here, which now instead of being a plane wave, it's just going around it's in quantized e to the in, and calculate the overlap integral with plane waves of the Higgs and the Q standard model. So we did this just in the last few days, and we got this result for the decay rate. So this is a little concerning for Forton lovers because L loop is like a 1,000 over FA. So if you substitute it here, and here is the FA. So basically, it seems like the decay rate is always shorter. Sorry, the lifetime for the decay of a single zero mode is always shorter than the age of the universe for a Yukawa that's larger than 10 to the minus 15, which is what we needed in order for the KSVZ fermions not to be stable in the early universe. However, we still need to evaluate the lifetime of the Vorton. So this is just the rate for a single zero mode decaying off the Vorton. And we're trying to think, and I bet we can also discuss this later, what's the lifetime of the Vorton itself? So this potentially could mean that there are no stable Vortons for, at any point of our parameter space, just because of this lower bound on Y. But I'm a little hesitant to say that conclusion, and the jury is still out on this one. All right, let's get to Axion strings in a primordial magnetic field. So without further ado, I mean, these things are going to be very clear for some people in the audience. There's an observational lower bound on the intergalactic magnetic field today of around 10 to the minus 16 Gauss, but also it has to be space filling. So the correlation length for the intergalactic magnetic field has to be more than 0.1 megaparsec. And this is from the non-observation of secondary gamma rays from TV blazars. And because of this lower bound on the intergalactic magnetic field, and also the thought that the galactic magnetic field was created by some dynamo that was fed by the intergalactic magnetic field, we're led to consider the primordial origin of the magnetic field, and a lot of people have talked about it, including people in the audience. Now, we don't assume a specific mechanism for the creation of the magnetic field. What we do is we scan over the possible values today, and we extrapolate into the early universe by this work by Banerjee and Jadamsik, which tells us how the magnetic field and its correlation length redshift in the early universe. And note here that there's some mismatches in conventions. So the spectral index, sometimes it's given by n, sometimes it's given by n minus 3. So here we follow the review by Durer and Naranov from 2013, where alpha, the redshift of the co-moving, so tilde means co-moving here, of the co-moving magnetic field goes like this, as a function of the spectral index. And n is kind of the minimal spectral index of the MHD plasma coupled to the magnetic field and the magnetic field itself. And this formula is derived as usual from the processing of the largest eddy, etc., etc. Good. So we want to scan over the magnetic field today. We want to scan over the magnetogenesis temperature in case it comes from a phase transition in the early universe. And we want to look at two kinds of magnetic field. We want to look at the compressible non-helical kind, which is what Banerjee and Jadamczyk were looking at, and also the helical case. And for both cases, the limit, the observation limit on the correlation length is more stringent than the limit on the value of the intergalactic magnetic field itself, which gives us a lower bound on B naught of 10 to the minus 13 rather than 10 to the minus 16. And we use standard formulae to interpolate both the co-moving magnetic field and the co-moving correlation length to the early universe. Okay, so what do we solve? We don't have a huge string simulation. We're just going to use the velocity-dependent one-scale model. And the key ingredients here are the correlation length, which also represents the curvature radius of the strings and the interstring distance. We also have the velocity on the strings. And the new ingredient that we have is we have the friction force due to the current, and we also have an equation for how the current grows. So these are the different elements, right? There's the redshift on the correlation length. There's the loss of string length into reconnections, and there's the friction force. There's the acceleration of the string due to straightening, due to its curvature. And then there's the Hubble drag force and the drag force due to the current. And then there's the current growth equation that I showed you earlier. And just to remind you, the friction force goes like mu over I. And note that when we take the friction force here, we substitute not the I that we calculate here, but actually the root mean square I. So we account for the reduction. We just multiply I by the square root of the correlation length of the magnetic field over the Hubble scale. So let's see some results. So we start with either of two things. We either start with strings that are just in the scaling regime, or we start with strings that are slightly friction dominated, just because even before we turn on the primordial magnetic field, we have a current that's comparable to the temperature. But in this case, the initial number of strings per Hubble is not very different from the scaling value of order 1. And then we just assume some magnetogenesis. Second order phase transition, first order phase transition. We'll talk about inflation later in the talk. As soon as we turn it on, what we get is the current growth term is huge. It just immediately makes it grow to a maximal current. And the byproduct, because of the friction, is that the velocity drops from relativistic to highly non-relativistic. So that's the starting point. Now we see plots versus temperature. That's the starting point here. You see that it starts not from a relativistic, but from a highly non-relativistic velocity. And then it slowly accelerates. But the acceleration is very slow. So slow that reconnections are basically suppressed. And because reconnections are suppressed and also friction is suppressed, essentially what happens is that these strings enter a renewed stretching phase, and their number just grows, and it grows independently of the details of the current or the PMF, because now the velocity is so slow that between the initial temperature of, let's say, 1,000 GeV and this turnover temperature, the velocity is so slow that the drag force no longer influences anything, and the strings just stretch. So in this regime, we don't really care what the I is. And then the details of the magnetic field kind of matter once you hit this turnover and you cross over from the stretching phase into the plasma-dominated phase that Dimopoulos and Davis were talking about. But you see that when we hit 1 GeV, which is our cursory temperature for the QCD phase transition, you get a number of strings per Hubble, which is way, way larger than this order 1 scaling value. And this should have far-reaching consequences for the Axion relic density. So this is literally the crux of the talk. So if there are any questions about it, you're welcome to ask. Good.
Since,
Okay.
since no one else is asking, the what's the effect of the QCD phase transition on these photons?
On the vortons or on the long strings?
Well, on both. Is there any effect?
Yeah. It creates domain walls, and the domain wall string system collapses within one E-fold.
And how about the photons?
The vortons, that's a good question. So I think the vortons probably just stay.
What's the size of the photons?
It's here it's 1,000 over FA. But note that whether or not we have vortons depend on this Yukawa. And in this part of the talk, when I consider the PMF, I set the Yukawa order 1, so the current on the vortons just leaks away. And we calculated the vorton density also in the presence of the PMF. That's in my backup slides, and we saw that it's negligible if you take the Yukawa order 1.
Okay.
Yeah. So basically, it's kind of we have it both ways. We don't have vortons, but we do have a large effect on the network evolution. All right. So now the plots that I'm showing right now is what I care about now is a snapshot at the QCD phase transition, because that's what's going to influence the density of the relic density of the QCD axion. So I'm scanning over the parameters of my model. That's the magnetic field, intergalactic magnetic field today, and the magnetogenesis temperature. And what the contours are telling me is the number of strings per Hubble at 1 GeV. So basically this value here, scanned over my parameter space. And you see that throughout the parameter space, there's just a large enhancement. So I'm showing two cases here. This is the helical case, and this is the non-helical alpha equals 3/5 case. Here's there's a lot of the parameter space. If the magnetic field today is too large, then if you extrapolate back, you're gonna have that the magnetic field just dominates the universe at early times. So we just excluded that part of the parameter space. And note that there's one parameter here that I'm not varying. It's FA, and this is what I'm going to vary in the next slide. And sorry, not in the next slide, but soon. And the last thing that I want to address here is that we also consider a scaling variant PMF from inflation, and we consider it in a very simplified analysis. So the lower bound is 10 to the minus 16 Gauss, and we just assume that the co-moving magnetic field at each temperature T is the magnetic field today. And we assume that the current on the string starts after the leakage processes decouple. So these are results from the inflationary scenario. You see that also the number of strings per Hubble is greatly increased. And here I'm just scanning over the magnetic field today. And here I'm scanning over FA. Good. So in the little time that I have left, I'm going to tell you about the implications for the QCD Axion relic density. So to do that, we have to somehow convert from string density to Axion density. And this is a matter of ongoing research by many simulation teams around the world. In essence, um, what we're saying is that because we have so many more strings, we're bound to have like more Axion dark matter. The question is if it grows like linearly with the number of strings or as a square root, and we'll see that it goes roughly as the square root of the number of strings. So how are the Axion how's the Axion dark matter produced? What happens is that around the QCD phase transition, the Axion mass starts rising as this power until it reaches its value today. In parallel, what happens is domain walls get created and the string and domain wall systems shrink to zero. They also radiate, the string domain wall systems also radiate into axions, but here there's an argument by Villador et al. Why this axions from the string domain wall system is going to be subdominant to the axions that are radiated from the strings themselves right before the QCD phase transition. So here we're going to consider just the axions created from shrinking loops right before the transition. And when we talk about axion dark matter, we should differentiate between relativistic axions, which we don't consider as dark matter, and non-relativistic axions, which we do. So the axion dark matter is the integral over the spectrum in the axion field that goes all the way to its mass, and that's a time-dependent quantity. Specifically to assess the relic density today, we have to evaluate it at a given time called TL, which is the time in which this rho IR is equal to MA squared FA squared. This is this is just the time that they start redshifting like matter. And more details are found in the recent papers by Vergetto and Villador et al. So we need to know the co-moving spectrum. We need to know the rho of radiated axions from strings and its derivative with respect to energy and time. There's some debate because this is not something that you can get directly from our simple one-scale model. You got to assume something about the spectrum of radiated axions, and specifically you want to know how you're distributing your energy. Is it over a small number of very relativistic axions or a large number of IR axions? In this case, we follow the most recent analysis by Grugetto et al. They did simulations and they extrapolated results from them. And what they claim is, one, the integrated spectrum just goes like row string at a given time divided by time. They claim an IR-dominated spectrum, which is a matter of some debate because the simulations can only be done in the early regime after the PQ phase transition, and they're extrapolating them to the late times around the QCD phase transitions. And what they're showing is that even though the spectrum tends to be UV dominated in the regime where you do your simulation, it looks pretty clear that when you extrapolate it to what happens around the QCD phase transition, it's going to be highly IR dominated, which is good because more IR dominated means more axions. There's a delayed relativistic redshift up to this critical time where it starts redshifting non-relativistically. And eventually the conclusion of their analysis is that omega axion roughly goes like the square root of the number of strings per Hubble times this log, which is of order 70. Good. So what's the difference between them and us? They are assuming, they're not assuming, but from their simulations that don't involve superconducting strings, they're inferring an order 15 strings per Hubble, which is due to logarithmic scaling violation. We, on the other hand, have a PMF that leads to 10 to the 4 to 10 to the 6 strings per Hubble, so it's going to give way more axions. The spectrum might be different just because the correlation length of the strings is different, but for simplicity, we assume that it's the same. If you don't assume that it's the same, it might diminish our effect a little bit, but not a lot. And then finally, we want the spectrum normalization because our strings are slower, so they reconnect less, at least in the early stages of the evolution. So we got to multiply by some efficiency factor. And this efficiency factor is basically um, calculated by comparing our row string at a given time to an equivalent network with the same instantaneous row string, but which has no reconnections. And then the difference is the energy that goes into reconnections, and we assume that this energy that goes into loops eventually mostly goes into axions. So we can take this calculation, and which is the total instantaneous energy lost to axions, divide by what Villodoro or Gorgetto et al. Got for non-superconducting strings, and get an efficiency factor. And at early times, high temperatures, we see that because our strings are very slow, the energy radiated into axions is going to be highly suppressed. But then later we get closer to friction domination, and this efficiency factor becomes order 1. So it's not going to be a huge reduction. And this is the money plot. So for example, you can see that, what I'm showing here is the axion density divided by omega dark matter. And if it's larger than 1, then it's excluded. So this chunk of parameter space is just excluded by creating too many axions, including here. And the more interesting thing is now not to vary over B today and magnetogenesis temperature, but actually to vary over FA. So when we do that, we see that this part of the parameter space is excluded here and here. This is for helical and the helical and non-helical case. And finally, what we take is slices of the parameter space. So we take the two plots that you saw earlier, when we just slice here to give you a 1D plot for 3 different values of the magnetic field. And here we take just 3 slices here. And the interesting thing to learn from these plots is that, for example, in this chunk of the parameter space, if the magnetogenesis temperature is 1000 GeV, what you get is no matter what your FA is, you're always excluded by creating too much axion dark matter. So this is completely excluded. Like you can't have axion strings embedded in a PMF if the magnetogenesis temperature is 1000 GeV. That's basically the idea. Usually bounds kind of go away as you vary FA, but not in this case. Here's the same thing for inflationary PMF. And in this case, I drew the exclusion line here. So depending on the strength of the magnetic field today relative to the minimum value of 10 to the minus 16 Gauss, you see that some chunks of the parameter space, for example, if for 10 to the minus, maybe it's an unrealistic value, but 10 to the minus 10 Gauss today, you see that the whole thing is again excluded for all values of FA. But even if you, let's say, take 10 to the minus 14 for Gauss for the intergalactic magnetic field today, you see that the crosses here at FA around 10 to the 8, and there are lower bounds from stellar cooling on FA. So this part is also going to be excluded by a combination of stellar cooling bounds and this bound from creating too many axions. So, all right, that leads me to my conclusion. Axion strings are chiral superconducting due to anomaly inflow, and that was a well-known, but slightly a well-known secret. The The second thing is that it could create vortons, and these are chiral vortons. And their survival really depends on this Yukawa, which gives the um, lifetime of the KSVZ fermions to go to the standard model. And it's a question whether or not we can have stable vortons for realistic values of this Yukawa. But the possibility of vortons is a model independent prediction, though their density is not. The second thing is that if you just embed them in any kind of primordial magnetic field, they're going to develop maximal currents. We should still see whether or not the magnetic field is screened by the band states, though I don't think it is. So if it's not screened, that leads to a new dominant friction on the strings, which slows them down instantaneously as soon as the magnetic field is turned on in the early universe. And that, when you follow the evolution, leads to orders of magnitude, 10 to the 4 to 10 to the 6 more strings per Hubble at the QCD phase transition. And in some of the parameter space, that just means that the whole Axion strings plus PMF scenario is excluded for all values of FA. Thank you.
Thank you very much, Ofri. Very nice talk. Clap on behalf of everybody. So I guess Tan May has some questions still on the back.
I used to think that, at the QCD transition, all the strings would get connected by domain walls, as you said. So if I think of a vorton as a big giant loop, which is sort of stabilized by the current, I would expect that that too would get the string would get connected by a disk.
Mm-hmm.
And then the wall would pull on the string, and then the whole disk would collapse. And so the vortons would go away. That's not valid?
So yeah, of course, when there's a domain wall, it will add to the force that pulls on the vorton. But now it's a quantitative question, right? Because what it might do, it might change the stabilization radius of the vortons to be much smaller, because the current grows higher and the charge density grows higher. So they might just shrink to a new size.
Oh, okay.
And one other thing that they can do is they can fragment. So we think about it as a disk, but it could really like twist and entangle with itself, and eventually kind of fragment into many of these tiny little vortons, which are now stabilized in this new equilibrium.
Okay. Well, you covered a lot of ground in your talk. Some of the cosmology is quite complicated. Not fully understood, I think. But yeah, maybe the basic confusion that that I am not so familiar with is this question I asked earlier, that current can flow on the string, like radially into the string, but it can't go radially out. And that may well be because of some CP violation in that term or something, but I think it would be important to understand.
I mean, you should. One way to look at it is just look at the sign of the Goldstone-Wiltshire current. Okay, so this is the radial part of the current, right? So let's say A goes like theta. So to have a non-zero value here, okay, nu has to be theta, right? And then you need you want mu to be z along the string, right? So this is z theta, and if you just look at the signs, you see that the direction of this Goldstone-Wiltshire current is dictated by if A sorry, it's invariant to whether A warps in one direction or another around the string. So inevitably, you'll get that this term flows radially into the string, I think, and not outwardly.
I see. It almost sounds like a black hole where things can go in, but they can't go
Yeah.
out. Yeah.
I mean, at least here you know where they're going. They're just flowing along the string instead of getting lost in an island or something.
Yeah. Okay. All right. Well, I'll have to think more about it. Yeah.
Right, good. Do we have any more questions or comments?
Well, I have a question, not to myself, but to the audience. So, what do you think about the screening of the magnetic field?
Yeah, that's the question you raised. Yeah.
Yeah.
I think it would help if you could just sort of draw in sort of simple sketch. So maybe this is what the sketch is supposed to be.
Yeah.
That which way is the magnetic field going, and which
Yeah.
way?
So let's think about a different sketch. You have not, so here it's kind of horizontal, but let's think of a string aligned along the z-axis, and now that string is charged, and also there's current going in the positive z direction. And now you try to solve the Schrodinger equation in this background. So they're gonna be like 1D bound states just because there's a Coulomb potential around the string. So in this sense, it's pretty clear to me that it's true. You can put an electron there and it'll just stay close to the string. And eventually you can put a lot of them and they will they'll screen the electric field of the string. But now the question is, where are they moving along the z-axis?
But you'd only have electrons. There wouldn't be any positrons, right? Positrons get repelled.
Right. The positrons just fly away.
Yeah. So yeah, and why would the electrons be propagating along the string? And in which would they choose one direction?
Yeah, that's my question.
I think that one might be able to answer.
Yeah.
I don't see why the electrons. I mean, the electrons are not I mean, there's no CP violation, so the electrons can go up or down. It doesn't matter, right?
Right. That's what I think.
So I don't see a reason for them to cancel the current.
Yeah, that's my reasoning. Well, good. I'm gonna talk to these guys next week and see why they're saying the magnetic field is screened.
I mean, unless you have an E, which is radial, B, which is as a neutral, so you have an E cross B, which is sort of going along the string. Unless when you solve for the electron bound state, that also gets pushed by this, I don't know, electropointing vector. And maybe that gives you a current which is also along the string due to the electrons, and then that might cancel. I think one would probably have to solve this.
Right.
Yeah. It's a complicated problem because there's E, there's B, there's zero mode, there's a string.
Right.
Electron.
Yeah, exactly. So
Yeah.
that's what we're thinking about right now.
Yeah. Okay, well, lots of good physics.
Yeah, lots of stuff to do.
Yeah.